Synchronous motors, DC excitation and DC field switch operation. In this presentation, we're going to be looking at the methods that we have for DC excitation and the uniqueness around a DC field coil switch on a synchronous motor. As we remember, this is a simplified synchronous motor where we have a stator winding that is connected in either Y or delta and connected to the three-phase source, and we have a rotor coil that is connected to a DC source also. There are three different ways primarily that we can get DC voltage to the rotor coil. We have external DC source exciters, built-in DC exciters, and finally brushless DC exciters. An external DC exciter source is actually quite simple. We have a DC source that is, well, external from the synchronous motor, and it could be anything from a battery to an external rectifying circuit. In any case, it is a separate source that applies DC voltage to the rotor winding through a set of brushes. A built-in DC exciter is slightly different, and the way that we deal with this type of system, or the way that it's constructed, is essentially by coupling two separate systems that we already are quite aware of. First, on the left is the synchronous motor. On the right is actually a DC generator. Now, the DC generator is simply mounted on the same shaft as the rotor, or the field winding in the synchronous motor, and it's all sort of packaged together. And so we still have a couple of brushes, but the brushes are now actually coming off of the DC generator to supply voltage to the rotor. Finally, the last type is called a brushless DC exciter. There's a lot going on here, so we're going to take a look at it in different sections. The first thing I want to do is just divide it. And I'm going to divide it like this because we can start to see what items are going to actually be rotating on the rotor and which items are stationary and not moving. So stationary is at either end, and the items that are rotating on the rotor shaft itself, these are all turning inside the motor, are shown in the middle of the diagram. Well, let's start off at the far right-hand side of this diagram and look at each component and see how this provides DC to the field winding or rotor in our synchronous motor. The first item is this. It's a single-phase bridge rectifier. That's where we take AC single phase and we send it through an arrangement of 4 diodes in a bridge arrangement to give us a rectified DC output. So out of this rectifier, we have DC voltage which goes to the stator of something called a brushless exciter. Now, what a brushless exciter is essentially a mini alternator. And we're going to get into alternators in a couple of days, but a mini alternator is essentially something that generates AC. This is actually going to generate 3-phase AC. And that's because the rotor in this diagram has 3 separate windings that are separated by 120 degrees each. If the stator in this brushless exciter is energized with DC voltage and the rotor windings are moved or turned on a rotor, that would mean that there would be cutting of lines of flux. So since there's 3 rotor windings breaking magnetic flux, we generate 3-phase AC. And out of the left side of the brushless exciter, we see these 3 wires going to yet another bridge rectifier. So DC goes in, 3-phase goes out. Now we get to the 3-phase bridge rectifier, 3-phase AC goes in, and DC voltage comes out. Now remember, we have another series of diodes, and we're going to get into a 3-phase bridge rectifier system later in electronics. So at this point, it's not extremely important to understand the actual conducting order of these 6 diodes. So in doing this arrangement, there is now 0 brushes and 0 slip rings. And because there is neither of those, there is far less maintenance that is required on this type of synchronous motor. The DC field coil switch, or the switch that essentially connects the DC field coil to the DC voltage, is quite unique. And it's unique because it needs to overcome a couple of challenges. So, to back up, remember, an inductive DC circuit will generate a significant voltage kick when open circuited. And if we look at the diagram below, we can see a coil on the left or right-hand side, and it has been energized with a DC source, and it has approximately 12 volts across it. When I open this circuit, the joules of energy that have been stored in this inductor in magnetic bonds will immediately become greatly amplified. And there is quite a bit of theory behind it as to how it happens and where it happens and the interaction of collapsing magnetic fields, but the end result is that a significant voltage kick is generated by the opening of this DC circuit. And this can cause damage. Remember, the field coil in our synchronous motor is a coil, meaning it's an inductive. And it's going to be energized with DC, which means at some point it's going to have to be open circuited. So we can't have this happening. There must be a way for us to prevent this damage. On the other hand, when magnetic lines of flux are broken by a conductor, a voltage is induced. So this same coil, when it's not connected to the DC, when the motor is starting up, what's going to happen? Well, there's going to be a rotating magnetic field around that coil. And what's that going to cause? Well, it's going to cause an AC voltage to be generated on that inductive coil or the winding in the rotor. So AC volts will be induced across the inductor. Both of these situations can be damaging as soon as we start closing and opening switches. You don't want to take 30 volts AC and immediately connect it to a 12 volt DC source. The DC field switch operation is designed to prevent both of these situations from damaging the system. During startup, the field coil is short-circuited with a resistor. This prevents AC voltage from building up on the winding due to the rotating stator magnetic flux. To synchronize, the field coil is energized with the DC source, but while the resistor is still connected. The resistor is then disconnected after. To desynchronize, the resistor is first reconnected to the field coil while the DC is still connected. This prevents the generation of a DC inductive kick when the DC is disconnected. And finally, the DC voltage is disconnected. Well, let's see how this actually plays out with the switch. So here we're going to start a synchronous motor. We energize the three-phase stator and we wait for the RPM to rise. At this time, the resistor is connected across the field winding. And this is what's reducing or limiting the AC voltage that's generated on the winding. Once we reach the required speed, we are going to want to energize this rotor winding with DC. And you can see the switch has now moved. The switch is now closed and we have DC voltage. However, this field discharge resistor, or the resistor in the connection, is still terminated across the winding. Now the switch mechanism moves with a linkage that disconnects the field discharge resistor from the rotor winding. So there are three distinct steps. It starts with the resistor connected. It then connects the DC voltage in addition to the resistor. And finally, the resistor is removed from the circuit. If we were to look at stopping a synchronous motor, well, we would then be looking at the motor being synchronized already, which means that DC voltage is being applied to the winding. The resistor is not connected across the field winding at this time, and so the very first step that will take place in the linkage system of this switch is that the resistor will be first connected back into the rotor circuit. Then, after full articulation or movement of the switch, the DC voltage will be removed. And due to the resistor being connected into this inductive loop, we will have low or almost non-existent DC inductive voltage kick. At this point, we would de-energize the three-phase stator and the RPM would drop to 0.